Fuel ash corrosion damage mechanisms as a part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of fuel ash corrosion based on API 571, Number A. Fuel ash corrosion is accelerated high-temperature wastage of materials that occurs when contaminants in the fuel form deposits and melt on the metal surfaces of fired heaters, boilers and gas turbines. Number B. Corrosion typically occurs with fuel oil or coal that is contaminated with a combination of sulfur, sodium, potassium and/or vanadium. Number C. The resulting molten salts, slags, dissolve the surface oxide and enhance the transport of oxygen to the surface to reform the iron oxide at the expense of the tube wall or component. Here's a comprehensive and detailed description of fuel ash corrosion damage. Detailed explanation and overview. Fuel ash corrosion, also known as slagging and fouling corrosion, is a high-temperature degradation process that occurs in boilers, incinerators, and other combustion systems where fuel combustion produces ash particles. When these ash particles deposit on heat transfer surfaces, they can cause significant corrosion damage, compromising equipment integrity and efficiency. Number 1. Nature and origin of fuel ash. Number A. Source of ash. Combustion of fossil fuels such as coal, biomass, or oil produces ash particles. The chemical composition of ash varies depending on fuel type but commonly contains oxides of silica or CO2, alumina or Al2O3, iron oxides or Fe2O3, calcium oxides or CaO, magnesium oxides or MgO, and trace elements like sulfur, sodium, potassium, vanadium, nickel, etc. Number B. Formation of ash particles. During combustion, inorganic constituents in the fuel vaporize and then condense as fine ash particles. These particles are transported by flue gases and tend to deposit on heat transfer surfaces. Number 2. Mechanisms of fuel ash deposits. Number A. Deposition. Ash particles impact and adhere to hot surfaces, especially in regions of low flow velocity or temperature gradients. Deposits can be loose or fused, depending on temperature and ash composition. Number B. Fouling and slagging. Accumulation of ash leads to fouling, thin layers, or slagging, thick, fused deposits. These deposits act as thermal insulators, reducing heat transfer efficiency and causing temperature gradients. Number 3. Chemical and physical aspects of fuel ash corrosion. Number A. Chemical composition of ash. The presence of alkali metals, Na, K, and alkaline earth metals, Ca, Mg, can cause fouling and fused slag formation. Sulfur compounds, SO2, SO3, react with ash components, forming acidic deposits that enhance corrosion. Number B. Fused deposits and molten salts. At high temperatures, typically 800 to 1200 degrees Celsius, ash can melt or partially melt, forming slag or molten salts. These slags can be acidic or basic depending on the composition, affecting how they interact with metal surfaces. Number C. Interactions with metal surfaces. Molten or semi-molten ash deposits chemically react with metal surfaces, especially if the metal is susceptible to corrosion. Reactions often involve the formation of complex salts and oxidation of alloying elements. Number 4. Corrosion processes in fuel ash corrosion. Number A. High-temperature corrosion. The deposits create localized chemical environments that promote corrosion. Acidic deposits, such as sulfur-rich, can attack protective oxide layers on steels and alloys. Number B. Alkali-enhanced corrosion. Alkali metals like sodium and potassium form alkali salts, such as Na2SO4, K2SO4, that are fluid at high temperatures. These salts can dissolve protective oxide layers, exposing fresh metal surfaces to further attack. Number C. Sulfur-induced corrosion. Sulfur reacts with metal surfaces to form metal sulfides. These sulfides are often less protective than oxides and can lead to spallation of protective layers. Number D. Fused salt attack. Molten salts penetrate microcracks and pores in oxide layers, causing intergranular corrosion. This process can lead to material thinning, cracking, and structural failure. Number 5. Types of fuel ash corrosion damage. Number A. Fouling. Formation of insulating ash layers on heat transfer surfaces, causes thermal inefficiency and hot spots that accelerate corrosion. Number B. Slagging. Fusion of ash deposits into molten slag that adheres strongly and can damage surfaces through thermal stress and chemical attack. Number C. Corrosive attack, chemical degradation of metal surfaces due to reactions with ash constituents, results in oxide layer destabilization, pitting, and general material loss. Number D. Material degradation and mechanical damage. Ash deposits and slags can cause thermal stresses, leading to cracking or spalling of protective oxide layers. The combined effects lead to reduced lifespan of boiler tubes and components. Number 6. Factors influencing fuel ash corrosion. The first. If the factor is coming from ash composition, the effect is higher alkali metals and sulfur increase corrosivity. The second. If the factor is coming from temperature, the effect is elevated temperatures promote melting in chemical reactions. The third. If the factor is coming from flow velocity, the effect is low velocities favor deposit buildup, high velocities can cause erosion. The fourth. If the factor is coming from oxidizing environment, the effect is promotes oxide formation versus corrosive salts. The fifth. If the factor is coming from metal alloy composition, the effect is certain alloys resist corrosion better due to stable oxide formation. Fuel ash corrosion damage is a complex process involving the deposition of mineral ash particles on high-temperature surfaces, where they melt or fuse into slag or salts. These deposits chemically interact with the metal surfaces, often facilitated by the presence of sulfur and alkali metals, leading to oxidation, sulfidation, and acidic corrosion. The damage manifests as material degradation, pitting, spalling, and loss of structural integrity, ultimately impairing heat transfer efficiency and risking equipment failure. Fuel ash corrosion damage affected materials based on API 571. Number A. All conventional alloys used for process heater and boiler construction are susceptible. Number B. Alloys of the 50Cr, 50Ni family show improved resistance. Here's a detailed explanation of the materials affected by fuel ash corrosion damage. Detailed overview. Introduction. Fuel ash corrosion predominantly impacts metallic materials used in high-temperature environments such as boiler tubes, heat exchangers, and combustion chamber components. The extent and nature of damage depend on the material's composition, microstructure, and protective oxide layers. Number 1. Commonly affected materials. Number A. Carbon steels. Description: low to medium carbon steels are widely used due to their cost-effectiveness. Vulnerability includes poor resistance to high-temperature corrosion, lack of protective oxide layers, highly susceptible to sulfidation, alkali salt attack, and oxidation. Carbon steel's damage characteristics includes rapid material loss, pitting and spallation under ash deposits, and formation of iron sulfides and other corrosive compounds. Number B. Alloy steels and cast steels. Description: contain alloying elements such as chromium, nickel, manganese, and molybdenum. Vulnerability: more resistant than carbon steels but can still suffer corrosion if the protective oxide layers are compromised. Alloy steels and cast steels damage characteristics: localized attack at microcracks, and formation of sulfides and alkali salts at high temperatures. Number C. Stainless steels, such as types 304, 310, 316, 321, 347. Description: contain chromium 10.5% and above and other alloying elements that promote oxide formation. Stainless steel's vulnerability: generally resistant to oxidation, but high-temperature environments with aggressive ash deposits can cause degradation of protective oxide layers. Susceptible to alkaline salt corrosion and sulfidation. Certain grades like 304 are less resistant than higher alloyed types like 310 or 347. Stainless steel's damage characteristics: spallation of oxide layers, pitting corrosion, intergranular attack if microstructural stability is compromised. Number D. Nickel-based alloys, such as Inconel, Hastelloy. Description: high-performance materials for severe environments. Nickel-based alloys vulnerability: generally, highly resistant, but prolonged exposure to molten salts and sulfur-rich deposits can cause internal and surface corrosion. Nickel-based alloys damage characteristics: formation of nickel sulfides, possible cracking under thermal stress. Number E. Refractory and special alloys, such as FeCrAl, T alloys. Description: designed for high-temperature corrosion resistance, vulnerability, less susceptible but not immune under extreme ash deposition and chemical attack. Number 2. Material microstructure and protective oxide layers. Number A. Oxide layer formation. Many alloys develop protective oxide films, such as Cr2O3 in stainless steels, Al2O3 in FeCrAl alloys, at high temperatures. These layers serve as barriers against further oxidation and corrosion. Number B. Impact of fuel ash. Ash deposits, especially those rich in alkali salts, Na2SO4, K2SO4, and sulfur compounds, can attack or destabilize these oxide layers. Molten salts penetrate oxide layers, causing spallation, exposing fresh metal surfaces. Number 3. Summary of specific material vulnerabilities and damage types. For material type is carbon steel, vulnerabilities is no protective oxide, damage mechanisms are sulfidation, salt attack, typical damage features are rapid thinning, pitting, spalling. For material type is low alloy steel, vulnerabilities is limited oxide stability, damage mechanisms are alkali salt corrosion, typical damage features are localized attack, pit formation. For material type is stainless steel, vulnerabilities is oxide layer degradation, damage mechanisms are pitting, intergranular corrosion, typical damage features are pits, oxide spallation. For material type is nickel alloys, vulnerabilities is salt penetration, damage mechanisms are sulfide formation, typical damage features are surface cracking, internal degradation. For material type is refractory alloys, vulnerabilities is high temperature stability, damage mechanisms are less affected, typical damage features are generally resistant, but can degrade under extreme conditions. Number 4. Factors affecting material susceptibility. Chemical composition, higher chromium, nickel, and aluminum contents improve resistance. Microstructure, fine-grained structures may resist creep and corrosion better. Surface condition, presence of protective oxide layers or coatings enhances durability. Operational temperature, elevated temperatures accelerate corrosion processes. Ash composition, presence of alkali metals, sulfur, and other aggressive elements increases vulnerability. Fuel ash corrosion primarily affects ferrous and some non-ferrous metallic materials, especially those lacking robust high-temperature protective oxide layers. The severity depends on the alloy composition, microstructure, operational environment, and ash chemistry. Proper material selection, favoring corrosion-resistant alloys, and operational controls are vital to mitigate such damage. Fuel ash corrosion critical factors based on API 571, Number A, the concentration of molten salt forming contaminants, metal temperature and alloy composition are the critical factors. Number B, the severity of damage depends on the type of fuel, such as the concentrations of contaminants in the fuel, sulfur content and metal temperature. Corrosion occurs by this mechanism only if the metal temperature is above the temperature of the liquid species formed, and it is most severe where the temperatures are the highest. The corrosion rates differ depending on the alloy and location within the heater. Number E, the liquid species, slags, are different for the oil and coal ash and are also different for water wall tube corrosion. Number 1, for oil ash, the liquid species are mixtures of vanadium pentoxide and sodium oxide, or vanadium pentoxide and sodium sulfate. Depending on the precise composition, melting points below 1000 degrees Fahrenheit or 538 degrees Celsius are possible. Number 2, for water wall corrosion, the liquid species are mixtures of sodium and potassium pyrosulfates that have melting points as low as 700 degrees Fahrenheit or 371 degrees Celsius. Number 3, for coal ash, superheater and reheater corrosion is caused by sodium and potassium iron trisulfates that melt between 1030 degrees Fahrenheit and 1130 degrees Fahrenheit or 544 degrees Celsius and 610 degrees Celsius, depending on the ratio of sodium and potassium. Reducing conditions, that is, a flue gas rich in carbon monoxide, hydrogen sulfide and hydrogen will aggravate the corrosion rates. Number F. Unburned coal particles also add carbon to the fly ash deposits and provide a reducing environment on the tube surface where corrosion occurs. Carburization of the tube surface, especially on austenitic alloys, will decrease corrosion resistance and increase tube wastage rates. Number G. Corrosion rates under reducing conditions may be 2 to 5 times faster than under oxidizing conditions. Here's a comprehensive and detailed explanation of the critical factors influencing fuel ash corrosion damage. Detailed explanation. Introduction. Fuel ash corrosion is a complex process influenced by multiple interacting factors. Understanding these factors is essential for predicting damage, designing resistant materials, and implementing effective mitigation strategies. Below are the key factors that critically affect the severity and progression of fuel ash corrosion. Here's a comprehensive and detailed explanation of the critical factors influencing fuel ash corrosion damage. Number 1. Ash composition. Number A. Presence of alkali metals, Na, K. Alkali metals form low melting point salts such as Na2SO4 and K2SO4. These salts can fuse or partially melt at high temperatures, creating molten or semi-molten deposits. Molten salts penetrate oxide layers and attack underlying metals, promoting corrosion. Number B. Sulfur content. Sulfur in ash forms metal sulfates, such as Na2SO4, K2SO4. Sulfates can react with metal surfaces to form metal sulfides, which are typically less protective than oxides. Sulfur enhances acidic corrosion and accelerates oxide layer breakdown. Number C. Mineral and metal oxides. Ash contains oxides like CO2, Al2O3, Fe2O3, Chao, MgO. These components influence the melting behavior and reactivity of the ash deposits. Number D. Trace elements. Elements like vanadium, nickel, and chlorides can catalyze corrosion reactions or form volatile compounds that exacerbate damage. Number 2 of critical factors influencing fuel ash corrosion damage is temperature. Number A. High operating temperatures. Elevated temperatures, typically 800 to 1200 degrees Celsius, promote the melting or softening of ash deposits. Higher temperatures accelerate chemical reactions, including oxidation and sulfidation. The melting point of ash components determines whether deposits are solid, semi-molten, or fully molten. Number B. Temperature gradients. Variations in temperature across surfaces cause thermal stresses. Hot spots can localize corrosion and facilitate spallation of oxide layers. Number 3 of critical factors influencing fuel ash corrosion damage is deposit characteristics. Number A. Deposit thickness and morphology. Thicker deposits provide insulating layers, leading to temperature increases beneath deposits. The morphology, porous, fused, or layered, determines how easily corrosive agents penetrate. Number B. Fusibility and melting behavior. The fusing point of ash components influences whether deposits are solid or molten. Fused deposits trap corrosive salts against the metal surface, intensifying corrosion. Number 4 of critical factors influencing fuel ash corrosion damage is chemical environment. Number A. Presence of molten salts. Molten alkali salts act as chemical corrosives, dissolving oxide layers and exposing fresh metal. These salts can penetrate microcracks and accelerate localized corrosion. Number B. Acidic versus basic conditions. Sulfur and chlorine compounds can create acidic environments that attack protective oxide layers. Basic environments may promote oxidation but can be less aggressive. Number C. Oxygen availability. An oxidizing environment promotes the formation of protective oxide layers. However, fluctuations in oxygen levels can lead to oxide layer destabilization. Number 5 of critical factors influencing fuel ash corrosion damage is metal and alloy properties. Number A. Alloy composition. Presence of chromium, nickel, aluminum, and other elements enhances oxide layer stability. Alloys with high chromium content form chromia, Cr2O3, which resists corrosion. Number B. Microstructure. Fine-grained and homogeneous microstructures tend to resist corrosion better. Microcracks or porosity can allow ingress of corrosive agents. Number C. Surface condition. Clean, smooth surfaces with intact oxide layers are more resistant. Surface contamination or roughness can trap ash deposits and promote corrosion. Number 6. Operational factors. Number A. Flow velocity of flue gases. Low flow velocities favor deposit accumulation. High velocities can cause erosion but may remove deposits, reducing corrosion risk. Number B. Cleaning and maintenance. Frequent cleaning prevents ash buildup. Inadequate cleaning allows thick deposits to develop, increasing corrosion potential. Number C. Fuel quality. Fuel with high mineral content or impurities increases ash formation and corrosive potential. Number 7. Environmental and system factors. Number A. Presence of chlorides and other volatile elements. Chlorides can break down oxide layers and promote pitting corrosion. Volatile elements condense on cooler surfaces, forming corrosive deposits. Number B. Temperature fluctuations. Rapid cooling or heating cycles cause thermal stresses, leading to cracking of oxide layers. Number C. Material thickness and design. Thinner materials are more susceptible to penetration of corrosive agents. Design features that trap deposits exacerbate corrosion. Summary table of fuel ash corrosion damage critical factors. If the critical factors is coming from ash composition, its influence determines melting point and chemical aggressiveness, then its effect on corrosion severity is high alkali or sulfur content increases corrosion risk. If the critical factors is coming from temperature, its influence affects ash melting and reaction rates, then its effect on corrosion severity is higher temps promote melting and chemical reactions. If the critical factors is coming from deposit characteristics, its influence thickness, porosity, fusion, then its effect on corrosion severity is thicker, fused deposits intensify damage. If the critical factors is coming from chemical environment, its influence salts, acidity, oxygen, then its effect on corrosion severity is acidic, molten salts accelerate corrosion. If the critical factors is coming from material properties, its influence alloy composition, microstructure, then its effect on corrosion severity is resistant alloys mitigate damage. If the critical factors is coming from flow velocity, its influence gas movement, then its effect on corrosion severity is low flow encourages deposit buildup. If the critical factors is coming from operational practices, its influence cleaning, fuel quality, then its effect on corrosion severity is regular maintenance reduces risk. Fuel ash corrosion damage is governed by a complex interplay of ash chemistry, operating temperature, deposit behavior, material properties, and system conditions. Controlling these critical factors, through fuel selection, operational adjustments, material choice, and maintenance, can significantly reduce the severity of corrosion and extend the service life of high-temperature equipment. Fuel ash corrosion affected units or equipment based on API 571, Number A, fuel ash corrosion can occur in any fired heater or gas turbine utilizing fuels with the aforementioned contaminants. Number B, fuel ash corrosion is most often associated with fired heaters burning vanadium and sodium contaminated fuel oils or residue. Number C, heater tubes are sometimes not affected because their skin temperatures are cooler than the threshold melting point of the slags in most heaters. Tube hangers and supports, however, operate hotter and can suffer severe fuel ash corrosion. Number D, some gas turbines suffer blade corrosion when switched over to burning fuel oil. Number E, in some cases, coking of the heater tubes may cause operators to increase heat flux that may push some components above the threshold temperature where fuel ash corrosion is possible. Number F, since the melting points of these liquid species are around 1000 degrees Fahrenheit or 538 degrees Celsius and higher in the superheaters and reheaters, any unit that has metal temperatures above the melting point of the sulfates may have the problem. Number G, for oil-fired boilers, fuel oils that do not contain vanadium are less prone to liquid ash corrosion. Number H, for water walls, if the temperature can be maintained below the melting point of the pyrosulfates, that is below 700 degrees Fahrenheit or 371 degrees Celsius, damage will be minimized. Thus, steam generating pressures below about 1800 psi are nearly immune. Here's a detailed explanation of the units and equipment affected by fuel ash corrosion damage, including how and why they are impacted. Detailed overview. Introduction. Fuel ash corrosion predominantly occurs in high-temperature components within thermal power plants, boilers, and other combustion systems. These units and equipment are exposed to aggressive ash deposits, high temperatures, and chemical reactions that lead to material degradation over time. Number 1 of the units and equipment affected by fuel ash corrosion damage is boiler components. Number A, boiler tubes. Location, furnace walls, superheaters, reheaters, economizers, and air preheaters. Impact, corrosion of tube surfaces due to ash deposits and molten salts. Formation of pitting, spalling, and wastage. Failure risks, thinning of tubes can lead to leaks or ruptures. Number B, furnace walls. Location, refractory-lined or water-cooled walls. Impact, ash deposits can cause corrosive attack on refractory linings. The thermal insulation can degrade, affecting heat transfer. Number C, superheaters and reheaters. Impact, these sections operate at very high temperatures and are susceptible to ash deposition and corrosion, leading to reduced efficiency and material failure. Number D, economizers. Impact, position downstream, they are exposed to ash-laden flue gases, which can cause corrosion and fouling, reducing heat transfer efficiency. Number 2 of the units and equipment affected by fuel ash corrosion damage is air preheaters or APHs. Location, preheating incoming combustion air using flue gases. Impact, ash deposits and molten salts cause corrosion and blockage of heat exchange surfaces. Damage can lead to inefficient heat transfer and pressure drops. Number 3 of the units and equipment affected by fuel ash corrosion damage is condenser and heat exchanger units. Impact, while primarily operating at lower temperatures, ash deposits can be carried over, causing corrosion, fouling, and reduced heat transfer efficiency. Damage is less severe but still significant in terms of operational efficiency. Number 4 of the units and equipment affected by fuel ash corrosion damage is flue gas ducts and chimneys. Impact, ash deposits can accumulate on duct walls. Molten salts or corrosive compounds can attack duct surfaces, leading to material wastage and structural integrity issues. Number 5 of the units and equipment affected by fuel ash corrosion damage is ash handling equipment. Number A, ash conveyors and silos. Impact, corrosive ash can cause material degradation of conveyor belts, hoppers, and silos. Corrosion can lead to leakage, blockages, and damage to mechanical systems. Number B, ash crushers and crushers. Impact, exposure to hot, corrosive ash causes wear and corrosion, reducing operational lifespan. Number 6 of the units and equipment affected by fuel ash corrosion damage is furnace and combustion chamber. Impact, the interior surfaces are exposed directly to hot gases and ash deposits. Corrosion and erosion lead to thinning, cracking, and structural failure. Number 7 of the units and equipment affected by fuel ash corrosion damage is catalytic and NOx control units. Impact, systems like SCR, selective catalytic reduction, units are sensitive to ash deposits. Corrosion and deactivation of catalysts can occur due to ash-related chemical reactions. Number 8 of the units and equipment affected by fuel ash corrosion damage is other auxiliary equipment. Fans, dampers, and valves exposed to contaminated gases or ash-laden environments can suffer from corrosion and mechanical wear. Additional insights. Location-specific impact. The severity of corrosion varies depending on the location within the system, with hotter zones like superheaters being more vulnerable. Cycle of damage. Deposits cause localized heating, which accelerates corrosion and can lead to thermal fatigue. Operational considerations. Poor fuel quality or inadequate cleaning increases the risk, impacting multiple units simultaneously. Fuel ash corrosion damages a wide range of thermal power plant units and equipment, especially those operating at high temperatures or exposed directly to ash-laden flue gases. Its impact ranges from material wastage and fouling to structural failure, emphasizing the importance of material selection, maintenance, and operational control to mitigate such damage. Appearance or morphology of fuel ash corrosion damages based on API 571, Number A, oil ash corrosion is manifested as severe metal loss associated with slagging. In some cases, corrosion rates of 100 to 1000 mpy may be experienced. Number B, metallographic examination and deposit analysis techniques can be used to verify the presence of fuel ash corrosion. Number C, for oil ash corrosion of superheaters and reheaters, the appearance of the ash deposit will be in at least two distinct layers. The important deposit is adjacent to the component, which will have a dark gray or black appearance at room temperature. As the liquid sulfates sinter the corrosion debris to the surface, a hard, glassy, tenacious scale is formed. When removed, the surface of the steel will have an alligator hide appearance, see Figure 4, 127 and Figure 4, 128, as shallow grooves will have penetrated the steel in a cross-hatched pattern. See Figure 4 127, the alligator hide morphology of liquid coal ash corrosion is evident when the dense, glassy deposit is removed. Mag. 2.4x. See Figure 4 128, in cross-section, the surface grooving is, in actuality, broad, V-shaped corrosion fatigue cracks. Mag. 100x, etched. Number D, for waterwalls, the cracks are predominantly circumferential and, to a lesser extent, axial. The overall appearance on the waterwalls is one of circumferential grooving. Number 1, after the liquid ash layer develops, the slush can only hold a certain weight of ash. When the weight is excessive, the slag is shed, exposing a bare, uninsulated tube to the heat flux of the firebox. The temperatures will spike on waterwalls, by perhaps 100 degrees Fahrenheit or 38 degrees Celsius, and the cracking is then similar to thermal fatigue. Number 2, the mechanism for the steam-cooled tubes is similar, except that the temperature spike is probably less and, therefore, the thermal fatigue damage is less severe. Number 3, the alligator hide morphology of superheaters and reheaters and the circumferential cracking on waterwalls in coal-fired boilers is caused by a similar mechanism. Number E, for coal ash, the appearance will be a smooth interface between a glassy slag layer and the metal. Here's a comprehensive and detailed explanation of the appearance and morphology of fuel ash corrosion damage. Detailed explanation. Introduction. The physical manifestation of fuel ash corrosion damage varies depending on the nature of the corrosion process, operating conditions, and the materials involved. Understanding these morphological features is crucial for diagnosing damage, assessing severity, and implementing effective repairs. Morphology and appearance of fuel ash corrosion. Number 1, general characteristics of fuel ash corrosion morphology. Surface roughness and pitting. Corrosion often manifests as rough, uneven surfaces characterized by localized pits or cavities. Layered deposits. Accumulation of ash deposits, often fused or semi-fused, creates visible layers or coatings. Cracking and spalling. Damage may include surface cracks, spalling, flaking off of material, or delamination. Color changes. Oxide layers or deposits can cause discoloration, such as black, brown, or white residues. Number 2, specific morphological features. Number A, deposits and fused ash layers. Appearance, thick, fused, or crust-like deposits on metal surfaces. Morphology, these deposits may be glassy, porous, or fused due to partial melting of ash components. Effect, these layers trap corrosive salts and impede heat transfer, further exacerbating damage. Number B, corrosion pits. Appearance, small, round or irregularly shaped cavities. Morphology, usually localized, these pits can range from microscopic to several millimeters in diameter. Mechanism, formed by microgalvanic cells or localized chemical attack where deposits concentrate corrosive agents. Number C, corrosion pits. Appearance: thinning of metal walls, often with undercutting around pits. Morphology: leads to rough, uneven surfaces with areas of material depletion, TS. Number D. Cracking. Appearance: fine or coarse surface cracks or lamellar fractures. Morphology: cracks may be intergranular, along grain boundaries, or transgranular, across grains. Cause: result from thermal stresses, oxide layer spallation, or internal stresses from corrosion pits. Number E. Spalling and flaking. Appearance: chunks or flakes of material detaching from the surface. Morphology: often associated with oxide layer failure or fuse deposit removal. Impact: exposes fresh metal to further corrosive attack. Number 3. Microscopic and SEM, scanning electron microscope, observations. Deposits: SEM images reveal fused salt crystals with amorphous or crystalline structures. Pits: micrographs show microcracks, intergranular attack, and metal dissolution. Oxide layers, characterized by columnar or granular structures, sometimes porous or cracked. Cracks: morphology of cracks shows intergranular or transgranular features, indicating the mode of failure. Number 4. Progression of morphological damage. Initial stage: formation of ash deposits and minor surface roughening. Intermediate stage: development of pits, localized corrosion, and oxide layer degradation. Advanced stage: extensive pitting, cracking, spalling, and material loss leading to structural failure. Summary morphological features of fuel ash corrosion: if the morphological feature is ash deposits, its typical appearance would be glassy, crust-like layers, and its underlying cause melting and fusion of ash salts. If the morphological feature is pitting, its typical appearance would be small, round cavities, and its underlying cause localized corrosive attack, often under deposits. If the morphological feature is cracks, its typical appearance would be fine or coarse lines, and its underlying cause thermal stresses, oxide spallation. If the morphological feature is spalling, its typical appearance would be flaking of surface layers, and its underlying cause oxide layer failure, thermal fatigue. If the morphological feature is material wastage, its typical appearance would be thinned, perforated areas, and its underlying cause continuous corrosion and erosion. Fuel ash corrosion prevention and mitigation based on API 571, Number A. Fuel ash corrosion can be prevented by blending or changing fuel sources, minimizing the contaminants, and by operating equipment so that hot components are below the temperature where molten deposits are formed. Number B. Proper burner design and burner management can help to reduce flame impingement and localized hot spots. Number C. In some cases, the characteristics and melting points of the slags can be changed by firing with low excess oxygen or by injecting special additives into the fuel. These changes can increase the melting point of the slags and reduce the tendency of the deposits to stick to metal surfaces or dissolve the protective oxide scale. Even with changes to reduce slag formation, corrosion may continue if metal surfaces are not cleaned to remove slag and corrosion products. Number D. Corrosion of some components, such as tube hangers and supports, can be minimized by changing to a 50% Cr, 50% Ni alloy, such as alloy 657. Designs of tube hangers may need to be modified to account for the lower stress rupture strength of the 50 Cr, 50 Ni alloys. Here's a comprehensive, detailed explanation of prevention and mitigation strategies for fuel ash corrosion damage. Detailed overview. Introduction. Fuel ash corrosion is a complex problem caused by high-temperature ash deposits, chemical reactions, and molten salts attacking metallic and refractory surfaces in power plants and combustion systems. Effective prevention and mitigation involve a combination of material selection, operational practices, design modifications, and maintenance strategies. Detailed overview of prevention and mitigation of fuel ash corrosion damage. Number 1. Fuel quality and combustion optimization. Number A. Use of low ash, low alkali fuels. Objective: reduce the amount of ash and corrosive salts, such as sodium, potassium. Implementation: select coal or other fuels with low ash content and minimal alkali metals. Impact, less formation of molten salts and fused ash deposits, decreasing corrosion potential. Number B, proper fuel preparation. Objective, achieve uniform fuel size and moisture content. Implementation, proper grinding and drying to ensure complete and efficient combustion. Impact, reduces unburned residues and minimizes ash deposition. Number C, optimized combustion conditions. Objective, maintain optimal temperature, excess air, and burnout. Implementation, use of advanced burners, proper air distribution, and control systems. Impact, complete combustion reduces unburned carbon and minimizes ash carryover. Number 2 of prevention and mitigation of fuel ash corrosion damage is material selection and coatings. Number A, high temperature resistant materials. Use alloys with high corrosion resistance, such as stainless steels, nickel-based alloys, thermal barrier coatings. Impact, these materials can withstand aggressive ash deposits and reduce wastage. Number B, protective coatings. Types, ceramic coatings, enamel, or specialized corrosion-resistant paints. Impact, act as a barrier to molten salts and corrosive gases, prolonging component life. Number C, refractory materials. Use refractory linings with high melting points and chemical stability. Impact, protect structural components in furnaces and combustion chambers. Number 3 of prevention and mitigation of fuel ash corrosion damage is design measures. Number A, component design for ease of cleaning. Implementation, incorporate access doors, tap holes, or removable panels. Impact, facilitates regular cleaning and removal of ash deposits. Number B, reduction of hot spots. Implementation, optimize furnace and heat exchanger design to ensure uniform temperature distribution. Impact, minimize localized melting and deposition. Minimize surface area of deposits. Number C, implementation, use of inclined surfaces, smooth finishes, and streamlined designs. Impact, reduces ash accumulation and facilitates cleaning. Number 4 of prevention and mitigation of fuel ash corrosion damage is operational strategies. Number A, regular cleaning and ash removal. Methods, mechanical brushing, soot blowers, water sprays, or dry cleaning. Frequency, based on operational experience, often scheduled during outages. Impact, prevents buildup of deposits that could lead to corrosion. Number B, temperature control. Objective, keep metal surfaces below critical temperatures where ash fuses or melts. Implementation, adjust combustion parameters, use insulation, and control heat transfer rates. Impact, prevents formation of molten salts and reduces corrosion rates. Number C, optimized flue gas treatment. Implementation, install electrostatic precipitators, ESPs, bag filters, or scrubbers. Impact, removes ash particles and salts before they deposit on critical surfaces. Number 5 of prevention and mitigation of fuel ash corrosion damage is chemical additives and treatments. Number A, salt suppressants. Use additives that neutralize or bind alkali salts. Impact, reduce the formation of corrosive molten salts. Number B, corrosion inhibitors. Use chemical compounds that form protective oxide layers. Impact, enhance corrosion resistance of materials exposed to ash deposits. Number 6 of prevention and mitigation of fuel ash corrosion damage is monitoring and inspection. Number A, regular inspection. Methods, visual, ultrasonic, or radiographic inspections. Purpose, detect early signs of corrosion, deposits, or cracks. Number B, temperature and deposit monitoring, tools, infrared thermography, deposit sampling. Impact, identify hotspots and areas prone to ash buildup. Number C, corrosion and deposit analysis. Purpose, understand the chemical composition of deposits and corrosion products. Impact, inform targeted mitigation strategies. Number 7 of prevention and mitigation of fuel ash corrosion damage is maintenance and repair. Number A, scheduled maintenance. Activities: cleaning, recoating, or replacing damaged components. Impact: extends equipment lifespan and prevents catastrophic failures. Number B, component replacement, when materials exhibit severe wastage or cracking. Impact: restores system integrity and performance. Number 8 of prevention and mitigation of fuel ash corrosion damage is advanced technologies and research. Number A, fused salt-resistant alloys. Development of materials specifically designed to resist fused salts. Number B, ash deposit detachment technologies. Use of ultrasonic or vibration methods to dislodge deposits. Number C, thermal barrier coatings, TBCs. Applying ceramic TBCs to insulate and protect metallic surfaces from high-temperature corrosion. Summary table of prevention and mitigation of fuel ash corrosion damage. If strategy taken is fuel quality control, its key actions is to use low alkali, low ash fuels. The expected effect is to reduce corrosive salt formation. If strategy taken is material selection, its key actions is to use corrosion-resistant alloys. The expected effect is to improve durability of components. If strategy taken is protective coatings, its key actions is to apply ceramic or specialized coatings. The expected effect is to act as barrier against deposits. If strategy taken is design optimization, its key actions is to facilitate cleaning, reduce hotspots. The expected effect is to minimize ash buildup and thermal stresses. If strategy taken is operational control, its key actions is to maintain optimal temps, regular cleaning. The expected effect is to prevent deposit fusion and corrosion. If strategy taken is flue gas treatment, its key actions is to install filters and scrubbers. The expected effect is to remove ash and salts before deposition. If strategy taken is monitoring inspection, its key actions is to regular checks. The expected effect is to early detection and intervention. If strategy taken is maintenance replacement, its key actions is to scheduled cleaning and repairs. The expected effect is to prevent escalation of damage. Preventing and mitigating fuel ash corrosion damage requires a holistic approach combining material science, operational practices, design improvements, and regular maintenance. Proactive measures significantly extend equipment life, improve efficiency, and reduce costly downtimes and repairs. Fuel ash corrosion damage inspection and monitoring based on API 571. Number A, visual inspection is usually sufficient to detect hot ash corrosion. Number B, metal loss is likely to be severe and the presence of a slag will be apparent. Number C, tubes need to be grit blasted in order to remove the tenacious glass-like ash deposit. UT examination may be useful to measure loss of thickness. Here's a comprehensive and detailed explanation of inspection and monitoring methods used to detect fuel ash corrosion damage. Detailed overview. Introduction. Early detection of fuel ash corrosion is crucial to prevent catastrophic failures, optimize maintenance, and extend the lifespan of combustion system components. A variety of inspection and monitoring techniques are employed, ranging from visual examinations to advanced nondestructive testing, NDT, methods. Number 1 of inspection and monitoring methods for fuel ash corrosion damage is visual inspection. Number A, purpose, to identify surface anomalies such as deposits, discoloration, cracking, spalling, and wastage. Number B, methodology, conducted during outages or scheduled maintenance. Use of borescopes or fiber optic cameras to access confined or high-temperature areas. Inspection of hot surfaces with infrared thermography for temperature anomalies. Number C, indicators of fuel ash corrosion. Deposits of fused ash or crusts. Discoloration indicating oxidation or chemical attack. Cracks, pits, or spalling of protective oxide layers. Material thinning or perforations. Number 2 of inspection and monitoring methods for fuel ash corrosion damage is ultrasonic testing or UT. Number A, purpose, to measure wall thickness and detect internal or surface flaws caused by corrosion and wastage. Number B, methodology, use of pulse echo or through transmission techniques. Portable ultrasonic gauges are applied to accessible surfaces. Ultrasonic thickness gauges provide precise measurements of remaining wall thickness. Number C. Application. Monitoring material wastage in boiler tubes, headers, and other critical components. Detecting internal corrosion, voids, or delaminations not visible externally. Number 3 of inspection and monitoring methods for fuel ash corrosion damage is radiographic testing or RT. Number A. Purpose: to visualize internal defects, corrosion penetration, or deposits within thick components. Number B. Methodology: use of X-ray or gamma-ray sources to produce images. Suitable for inspecting welds, thick walls, and internal deposit buildup. Film-based or digital radiography systems are used. Number C. Advantages. Provides a permanent record of internal conditions. Detects deep-seated corrosion or voids. Number 4 of inspection and monitoring methods for fuel ash corrosion damage is infrared thermography or IRT. Number A. Purpose: to identify temperature variations indicative of corrosion or deposit buildup. Number B. Methodology: infrared cameras scan surfaces during operation or shutdown. Hot spots may indicate deposit accumulation, localized corrosion, or hot spots due to thermal insulation failure. Number C. Application. Non-contact, real-time detection of thermal anomalies. Useful for large area screening. Number 5 of inspection and monitoring methods for fuel ash corrosion damage is deposit sampling and chemical analysis. Number A. Purpose: to analyze ash deposits for composition and corrosive potential. Number B. Methodology: physical removal of deposits using scraping or brushing. Laboratory analysis using X-ray fluorescence or XRF, inductively coupled plasma or ICP, or SEMEDS to identify chemical constituents, especially alkali salts like sodium or potassium. Number C. Significance. Correlates deposit chemistry with corrosion severity. Helps predict future damage and inform mitigation. Number 6 of inspection and monitoring methods for fuel ash corrosion damage is corrosion probing and electrical resistance or ER sensors. Number A. Purpose: to monitor real-time corrosion rates on critical surfaces. Number B. Methodology: electrical resistance probes are installed on or near susceptible areas. Changes in electrical resistance correlate with material loss over time. Number C. Advantages. Continuous, real-time data collection. Early warning of increased corrosion activity. Number 7 of inspection and monitoring methods for fuel ash corrosion damage is optical and endoscopic inspection. Number A. Purpose: to perform detailed visual examination of internal surfaces inaccessible to direct view. Number B. Methodology: use of borescopes or fiber optic cameras inserted through access ports. Inspection of furnace interiors, heat exchangers, and turbine blades. Number C. Application: detects deposit buildup, cracks, spalls, and pits. Number 8 of inspection and monitoring methods for fuel ash corrosion damage is advanced non-destructive testing or NDT techniques. Number A. Electromagnetic testing, detects cracks or corrosion-induced changes in electrical conductivity. Number B. Acoustic emission monitoring, detects sound waves emitted from crack formation or propagation during operation. Number C. Laser shearography and phased array ultrasonics, provide detailed imaging of subsurface flaws and deposit layers. Summary table of inspection and monitoring methods for fuel ash corrosion damage. If method in use is visual inspection, it is purpose for surface condition assessment. The key feature of this method is simple, rapid, requires access. This method typical use cases is to detect surface deposits, cracks, spalling. If method in use is ultrasonic testing, it is purpose for wall thickness, internal flaws. The key feature of this method is precise, portable. This method typical use cases is to measure wastage, internal corrosion. If method in use is radiographic testing, it is purpose for internal defect visualization. The key feature of this method is deep inspection, permanent record. This method typical use cases is to detect internal voids, deposits. If method in use is infrared thermography, it is purpose for surface temperature anomalies. The key feature of this method is non-contact, real-time. This method typical use cases is to detect hot spots, deposit buildup. If method in use is deposit sampling and analysis, it is purpose for chemical composition. The key feature of this method is laboratory, destructive. This method typical use cases is to assess corrosive salts, predict damage. If method in use is corrosion probes and ER sensors, it is purpose for real-time corrosion rate. The key feature of this method is continuous monitoring. This method typical use cases is to early warning during operation. If method in use is endoscopic inspection, it is purpose for internal visual assessment. The key feature of this method is access via small openings. This method typical use cases is to detect deposits, cracks internally. If method in uses is advanced NDT, it is purpose for subsurface flaw detection. The key features of this method is high sensitivity. This method typical use cases to detect hidden flaws, deposits. A comprehensive inspection and monitoring program employing multiple techniques provides the best understanding of fuel ash corrosion damage. Regular visual inspections combined with advanced NDT methods enable early detection of deterioration, inform maintenance decisions, and help prevent catastrophic failures. Thank you.